Okay, this is our last derivatives topic. It's called related rates. Now, these are going to be word problems that deal with variables changing at certain rates. So keep in mind that a derivative is really what we call dy dx. Now, what this really means is the rate that y changes with respect to x. We're going to see lots of different rates, not just dy dx, but understand that what is in your numerator really means what's changing, and what's in your denominator is what it's with respect to. Now, in these related rates questions, it's always going to be with respect to time. So things are changing as time goes on. We'll see several examples in a little bit. And I've broken this up into level 1, level 2, and level 3. Level 1 is the easier types of examples, and then we'll get to more complicated ones after. So here are some general steps for you. If possible, try to draw a picture and label the fixed parts. You'll see that in these problems, there's certain things that are not always fixed. Okay. You want to identify the rates of change, all right, the ones that are known and whatever it is you're trying to find. You're going to have to write an equation of some sort relating all of the quantities. Now, you know there's no formula sheet in this course at all. So it's possible that you might have a situation in a problem that deals with the volume of a shape. So here are some formulas to be aware of in case they pop up. So volume of a cylinder, this is pi r squared h. If you remember that a cone is a third of a cylinder, it's pretty easy. It's just 1/3 pi r squared h. And then a sphere is 4/3 pi r cubed. Okay, so be aware of those formulas in the event it's a volume related rates word problem. So once you have an equation such as volume, for example, you are going to differentiate both sides with respect to time. All right, so that means in our denominator we're going to have a dt. Okay, up top you're going to have d something, whatever we're talking about. Maybe it's volume, maybe it's area, maybe it's surface area. All right, and so the piece about with respect to time, that's kind of like dx, except it's always with respect to time, not x, so we write dt. Then you're going to solve for whatever the unknown rate of change is, and then plug in appropriate information as needed. So come back to these steps as we look at examples here, and I'll kind of walk you through it. It'll make more sense as we go. Okay, so here's our first example for you to jot down. We want to know how fast is the area of a square increasing at the instant when the sides are 4 feet long if the sides increase at a rate of 1.5 feet per minute. So try to visualize this. We have this square, and let's give it a side length of s. We know that all the sides are equal in a square. And we're trying to find how fast the area of the square is increasing. So we are looking to find dA dt. That means the rate at which the area changes with respect to time. Now, we know that the sides are increasing at a rate of 1.5 feet per minute. So that means that ds dt is equal to 1.5 feet per minute. So it's a positive rate because it's increasing, we're told. If it were decreasing, we would make it a negative. And so understand this means that for every minute that goes by, the sides grow by 1.5 feet. Okay, so at the moment, at the instant when s is 4, we want to figure out how fast was the area changing at that instant. So what we need to do is write an equation relating the information here. So what are we talking about in this problem? Well, we're talking about area of a square, okay, and we're talking about the side of the square. So we write a general equation. Area is equal to side squared, right? You know that. So that's our equation that relates all of the pieces. Now we're going to take the derivative of each side. All right, now the derivative of a, before we've written it as a prime. Well, now we're going to write it as just dA dt. Think of it as before when we found the derivative of y, we said that's the same as dy dx, right? So dA dt means the derivative of a with respect to time. And then over here, you're just going to follow your same rules as before for derivatives. The derivative of s squared is 2s, and this is with respect to s, So, or with respect to time, so we need a ds dt on the end there. So basically whatever the letter is, we need to tack on d of whatever that letter is, and then dt because it's with respect to time. Okay? So from there, we're going to plug in the pieces that we know. So we're trying to find dA dt. So the moment that we're interested in is the instant when the side is 4. So this is where we're going to put 4 in for s, and then the rate of change here, ds dt, we're told that's 1.5. So when we clean that up, we're going to get 12. And now let's make sure we include a unit here. We're talking about the rate at which the area is increasing. Well, if it's area, we know we need feet squared. Okay, so we need square units, so the unit is feet, so square units per minute. Okay, so the square's area is increasing by 12 square feet every minute that goes by. So this would be our final answer. Okay, here's our next example. We're talking about a circle. And within this circle, we know we have a radius. Okay, so we'll label that R. And we're told that the radius of the circle is increasing at a rate of 2 inches per minute. So as soon as you read that, translate it, write it down on your paper. So dr dt, right? It's the rate. Circle that keyword. The rate at which it's increasing would be 2 inches per minute. All right. Again, positive because of the word increasing. Find the rate of change of the area. So make sure you're writing down the rate you're trying to find. So dA dt. When the radius is 6. All right. So I am not going to label 6 on my picture because my picture here, my circle, is growing. Okay. This is just the instant that we're interested in as far as finding the rate at which the area is changing. Okay. So we're not going to label that 6 on our picture. Okay. So we need to come up with an equation that relates all of these variables. So hopefully you're thinking, okay, area of a circle, that's an easy one. A equals pi r squared. So now take the derivative of each side. So dA dt equals, so I'm going to multiply that 2 down. Remember, pi is just some number. So multiply the 2 down to the pi. You'd have 2 pi times r. The r is really to the first. We don't need to bother to write that one. And then we need to tack on a dr dt. Okay, so that is our derivative. And then our last step is to plug in. So dA dt, that's what we're trying to find. So we have a 2 pi, and the r value of interest is 6. So that's the only time we're going to use that 6. All right, it's at the very end here. And then the rate is 2. So when we clean this all up, we get 24 pi. And remember, we're talking about a rate for the area. So the rate of change here for the area. And again, units are crucial, guys. You will get points off if you're not remembering your units. Okay. So 24 pi square inches per minute. That's a nice exact answer. If it's multiple choice, you might see the answers left in exact form. Or, if you were to throw that into your calculator, 75.398 would be an approximation. Okay, so either that or that would be your final answer. On to the last one. Okay, now we have a spherical balloon. So I'm not going to go too crazy trying to draw this. All right, so we have this balloon, and we're talking about it being inflated at a rate of 10 cubic centimeters per minute. It's talking about the radius. So this is obviously difficult to do, but we're talking about a 3D image here. All right, a sphere. So we have this balloon, and we're told that the rate, all right, so circle that keyword, of which it's inflated is 10 cubic centimeters. So what this is really telling us here is that dV dt, so that's the volume, the rate at which the volume is changing is 10 cubic centimeters per minute. All right, so look for that keyword cubic. Anytime you see that in a problem, it's really giving you the volume. All right, We want to know how fast is the radius increasing. So that means we're looking to find dr dt. Okay, these are always with respect to time. You're always going to have a dt in the bottom. And we're looking to do this when the radius is 5. Okay, so we need a formula for the volume of a sphere. Well, earlier we said that the volume of a sphere is 4/3 pi r cubed. So once you've established that, we're then going to take the derivative of each side. So the derivative of v is dv dt. And now I'm going to multiply this 3 down to the 4/3. When I do that, the 3's are going to cancel. I'm going to be left with just 4 pi and then r squared, and then don't forget to tack on a dr dt. Okay? So from there, we're going to plug in. Well, this time we know dv dt, and the r value of interest is 5, and we're trying to find dr dt. Okay, so I come up here to get my dr dt alone. Let's see, we do 5 squared, so that's 25 times that 4. So we're going to have 10 all divided by 100 pi, which you can say is 1/10 pi. Okay, so it's possible you might see that as your answer choice, or you might see, and let's not forget our units here. So this is the rate at which the radius is changing. So it's not going to be square or cubic inches, it's just going to be, or centimeters rather, it's just going to be centimeters per minute. Okay, so nothing squared or cubed. And then this is approximately, if we were to use a calculator, 0.032 centimeters per minute. So those are some basic lower level related rates questions. In the next video, we'll tackle some what I call level 2 questions.